Welcome back. In this section, we'll be talking about solving linear equations. Just to clarify, an equation would be a mathematical statement that involves an equal sign. If it doesn't have an equal sign, it's not an equation. So something like 3x minus 5 would not be an equation. 3x minus 5 equals 2, that would be an equation. And when something is an equation, you can solve to find out what would be the values of the variable or variables that satisfy the equation. When we say satisfy, we're looking for the values of the variable that would make the left side of the equation equal to the right side of the equation. And any value of x that does that, that satisfies the equation, would be a solution. The collection of all of our solutions, that would be the solution set. So for something like this equation x minus 1 times x minus 2 equals 0, you can confirm that there are two solutions, that when x is 1 or when x is 2, that would make the left side and the right side of the equation equal to each other. So you could say that the solution set contains the two values 1 and 2. When we're expressing things in sets, notice that we're going to be using curly brackets around our sets. So whenever we see those kind of brackets, that's referring to a set or a collection of things, in this case a collection of solutions. Now there's a bunch of things that you can do when you're solving an equation, and all of this should be hopefully very old news. One thing would be to simplify one side of the equation, rewriting it with something that's equivalent. You could add the same amount to both sides, divide the same amount from both sides. You could switch the two sides of the equation, or you could multiply and divide both sides. Now, the one little thing to keep in mind here is that when we're dividing or multiplying both sides of the equation, we'll be multiplying or dividing by some expression that's not 0. Of course, if you're multiplying by a constant, that's fine, but if you're multiplying by something that involves x's, then you're going to need to think about the fact that the thing that you're multiplying by or dividing by could potentially be equal to 0. So we're going to need to be a little bit careful when it comes to multiplying and dividing both sides of the equation. But for adding and subtracting, we can add or subtract whatever we'd like to both sides. So if you were solving this equation, you could say, well, I'll simplify the left side by first expanding 2 times 5x minus 4. And then maybe you might, again, simplify by replacing with something that's equivalent. Negative 8 plus 2, that's negative 6. You could add 6 to both sides of the equation. You could subtract x from both sides of the equation. Simplifying 10x minus x to give me 9x, and then to solve for what x is, I could divide both sides of the equation by 9. Now, since I'm dividing by something that's not 0, then I'm fine, that's good to do, and I can solve and find that x is 3/9, which in simplest terms would be 1/3. So my solution set would contain just a single value, 1/3. Now, one thing that we can do, and I didn't leave myself enough room to do it here, would be that you could check your solutions. If you wanted to check your solutions, you would do so by asking yourself what happens when you put in that value of 1/3 into the left side and also into the right side of the equation. Does it make the left side and the right side equal to each other? If it does, then you have confirmed that yes, you did find the solution correctly. If it doesn't, then that means what you found is not a solution and that something had happened, and you might need to think about why you came up with something that actually is not a solution. We will see in some cases there are kinds of equations where we can create what are called extraneous solutions, where we can find something, but it turns out not to solve the original equation. This kind of equation, however, which we're going to call a linear equation in a short period of time, is one where if we find a solution, it should be a solution of the original equation, and we can certainly check that. Now, the place where extraneous solutions can come into play, at least at this point in our life, would be when we're thinking about, again, multiplying or dividing both sides of an equation, and where we multiply or divide both sides of an equation by something that's potentially equal to 0. So I'm going to first solve an equation here and do it in a not particularly good way, and I'm going to wind up losing solutions, and I'm going to show you a correct way to solve this. So if you were thinking about solving this equation, x squared plus 2x is equal to 0. So if you were thinking about solving this, an incorrect approach might be to say, oh, I could divide everybody by x squared, 2x, and 0. I could divide everybody by x. That would leave me with x plus 2 equals 0. And I would come up with only one solution, and the solution would be x is equal to negative 2. Now, the reason why I'm saying that this is an incorrect approach, or one that's got a problem in it, is because when we did our dividing, we were dividing by something that potentially could have been equal to 0. If it turns out that x equals 0 is a solution, then by dividing by x, we have lost that solution. And I'll show you actually that 0 is a solution for this equation. If we were solving x squared plus 2x equals 0, I could factor x out, and we could find that yes, actually x is 0, or x plus 2 is 0, meaning that x is negative 2. So there should actually be two solutions in our solution set, not just negative 2, but 0 as well as negative 2. And when I decided to divide everybody by x, that wound up causing me to lose a solution. So when we divide by an expression that potentially could be 0, there is the possibility that you could wind up losing a solution. So again, we caution against dividing when you could be dividing by something that might take on the value of 0. The same is also true when you're multiplying an equation, both sides of it, by something that's potentially equal to 0. You could potentially introduce extraneous solutions to that equation. So, for example, something like this, if you were looking at solving it, you might say, oh, I could make my life easier by multiplying everybody on the left side and on the right side of the equation by x minus 1. And of course, on the left side, all of those x minus 1s would cancel. And on the right side, 0 times x minus 1 would just be 0. So you'd be left with x squared minus 1 is 0, and you could solve and find two solutions. That x is 1, or that x is negative 1. But just like with the last one, this approach has a problem. And the problem is this. If we were to look back at the original equation is not defined when x is equal to 1. If x were equal to 1, then you would have zeros in the denominator for both of these fractions. You would wind up having something that's undefined minus something that's undefined equals to 0. So one thing you know is that 1 could not be a solution. So that means here, this actually is extraneous. So x cannot be equal to 1, and that's because we know that the original equation would be undefined if x were equal to 1. Now, like I said, you could think about it that way. That would be one way to solve the problem. But another way, one that's maybe a little bit safer, would be this. Here, I'm just going to clear this out so I can show a second approach to solving the same kind of a problem. And that would be if you were to take this equation that we have and note that you've got two fractions, both with the same denominator, so you could combine these two fractions together. And that the numerator would factor. The x minus 1s would cancel. And we'd find that x is equal to -1. Again, we would only find one solution. And here, the actual only solution for this equation would be that x is equal to -1. So either way, either solving and then going back to think about the original equation, where is it not defined? What are those excluded values that we can't have for x? And then, of course, rejecting any solutions that involve that excluded value. Or we could try to solve without multiplying both sides of the equation by something that's potentially 0. But the moral of the story here is we should be particularly cautious anytime we're thinking about multiplying both sides of an equation by something that potentially could be 0 or dividing both sides. Then that's a potential place where we might wind up losing a solution or gaining a solution, and we're going to need to be particularly careful thinking about our answers. Now, a linear equation, this is one that's an equation where it's of degree 1. The highest power is just 1 on any variable that you have. And if we've only got one variable, then that means you would be able to rewrite it in that form. Something times x equals something. Here I'm assuming x is the variable that we're working with, but whatever variable it is, it could be written in that sort of a form. And of course, once it's in that form, then you can easily solve for what x is. So I'm going to solve a linear equation here, and I know it's linear because if we were expanding this out, we would see that the highest power of x is 1. There is no x squareds, there are no x cubes. This is strictly a linear equation. So expanding on the left side, we would have 1/3 times x plus 1/3 times 3 minus 2. On the right side, we would have 2/5 times 3x minus 1, 2/5 times 3x, which would be 6/5 x. And we would have 2/5 times minus 1, or minus 2/5. I'm not going to do as much writing as I did for the very first one, where I really split everything down into tiny, tiny little steps. I'm going to make things a little bit faster here. I'm going to move x's to one side and constants to the other, same way that I did before. So 1/3 x minus 6/5 x. And I've got on the right side minus 2/5 minus 1 plus 2. Now, as far as the simplification of things goes, this 1/3 minus 6/5, I mean, you certainly could do it by hand, I guess, if you had lots of time, but I'm not going to. I'm going to be using my calculator to do the fraction work here. 1/3 minus 6/5 being -13/15. And to see that in action, you can watch the video that I have on the course page about doing exponents and fractions using your calculator. It's a good skill to have because here, for example, even on the right side, something which is really not that bad, -2/5 minus 1 plus 2. I mean, you could make common denominators and do everything by hand, but you have a calculator that does this work for you, so why not? All right. So on the right side, I'd have 3/5, and now to solve, I would divide both sides of the equation by -13/15. So on the right side, I have 3/5 divided by -13/15, and that gives me -9/13. So there's my solution set. One thing I do want to mention before going any further, which is that, as is going to be a common theme throughout this course, I am only really interested in exact values. And by exact values, I mean values that have not needed to be rounded off or have had decimal places cut off. So, in general, that means that I will not be using decimals with very few exceptions throughout this course. So, for example, if you were to tell me the answer is, oh, about negative zero point 0.7, that's close to the right answer, but that exactly is not. The exact answer, negative 9/13, as a decimal, has infinitely many decimal places. There'd be no way to write it down without having to round something off or cut off a decimal place, which means if you tried to give your answer here using decimals, you are not giving the exact answer. You're giving an approximate value. And I am generally not interested in approximate values. So, one thing just to be aware of as we're going forward, any time that I want you to use decimals, I will tell you in the question, round your answer off to a certain number of decimal places. Then you can know, feel free, go ahead, write things as decimals, round things as appropriate. But otherwise, I want to see answers as exact values. So for example, if you were solving an equation and you solved and found that x was equal to square root of 2, that would be the answer that I would want to see. I would not want to see x is 1.414. That's not the square root of 2. It's almost the square root of 2 after it's been turned into a decimal and rounded off. That would not be the correct answer. So be aware of that as we go through the rest of the course, that unless I'm telling you explicitly to give me a certain number of decimal places, I do not want to see decimals. I want to see the exact value only. Now, of course, solving doesn't necessarily mean solving for a numerical value. It could just mean isolating an equation so it could be written in terms of that one variable. So here, solving for x means that we would like to rewrite this first equation as x equals rather than equal to c. One thing that we might want to make a little bit of a note here is that we can see already that x couldn't be equal to 0 because that would mean that you would have undefined fractions. You would have a over 0 and b over 0, and those would be undefined. So you maybe want to make a little bit of a note to yourself that x couldn't be equal to 0. And I'm making that note because maybe as I'm doing some solving, that fact might come into play. I don't know if it will, but we'll find out if it does. So the one thing I'll do here is I'm going to, and this is going to sound like I'm going to contradict what I said 2 slides ago, but I'm going to multiply both sides of the equation by x. Now it's potential that x could theoretically be equal to 0, but we've already made the notice for ourselves that actually, no, it can't. So if we do some work here and it turns out that x is equal to 0 at the very end of it all, we know that we'll need to reject that answer. That's the reason why we ask ourselves that question at the beginning. So with that in mind, I'm going to multiply every term by x so that I can now solve for what x is. Here I'm going to divide both sides of the equation by c. And so one other little thing that you can see here, number one, it told us in the story that c can't be equal to 0, and of course that makes sense because if c were equal to 0, then our answer here would have been undefined. But one other little fact that we know is since x cannot be equal to 0, then a plus b can't be equal to 0. So in other words, a cannot be the opposite of b. So if a were 5, b couldn't be negative 5, otherwise you'd wind up with something undefined. So nice to think about these sorts of things. This little bit of business that we have to do, thinking about when is an equation defined, when is it not defined, that is important because as we're going to see as we go throughout the course and learn all sorts of different kinds of functions, there are restrictions for some functions for what values of x they're allowed to take on. And so we'll be needing to think about those sorts of things. Okay, for this last one here, I have to solve for r, and so what I'm going to do is just expand what I have on the right side of the equation P times 1 is P times RT is PRT. And I'm solving for R, so I'll keep the PRT on the one side of the equation. And now I'll divide both sides of the equation by PT. So I'll be left on the right side of the equation with R, and on the left side of the equation, A minus P over T. So one thing that we can get out of this is that T can't be 0. So a little bit of a note for ourselves here. If we want to be able to solve for R, then that means that T can't be 0. All right, just a nice little word problem moment here. So here we've got a chemist has 2 liters of a solution that is 10% sulfuric acid. So we have one solution here that is 2 liters in total, but for the acid content, it's only 10% acid. And we want to take another solution that's made out of 20% sulfuric acid. We don't know how many liters we're going to take of that one. That's the mystery that we don't know. And that when I combine these two together, I'm going to get something that is going to have exactly 1 liter of sulfuric acid in it. So we have to be a little bit careful when we're reading things. This is one of the places where word problems can be difficult. Is we have to think about what exactly is it that we're looking to solve, what do we know, and how do these values relate to each other. One thing that's important to notice here is that we're using liters to refer to 2 different kinds of things. When I say 2 liters, I'm talking about the total amount of fluid is 2 liters. But since it's only 10% of that is acid, the actual amount of acid that's in this would be 10% of 2 liters. So 10% of 2 liters would be the amount of acid that we actually have from that first solution. And 10% of 2 liters is 0.2 liters. So of the 1 liter of acid that we want to get at the end, we have 0.2 liters of that 1 liter at the end. What are we looking to find? We want to know how much of the 20% solution do we need to add to it to get 1 liter of acid in total. So this is where I'll begin. I'm going to start by defining my variable here. I'm going to say that x is going to represent the number of liters of the 20% solution. And one thing that we said at the beginning was we want to have 1 liter of sulfuric acid at the end. We have 10% of the 2 liter solution. We're going to have 20% of the x liters, that's the 20% solution, and together the amount of acid that we want to have is 1 liter in total. So we have 2 liters of solution, 10% of that is acid, which means you really have 0.2 liters of acid. You have x liters of solution, 20% or 0.2, that's the proportion that's acid. So 0.2x, that's the amount of acid that we get from the second solution. Acid from the first solution, acid from the second solution needs to add up to give us 1 liter in total. So now we can solve for what x is. And so as it turns out, I will need 4 liters of the 20% solution. One thing to also notice here, I didn't just end with the number 4. I want to, anytime that there's a word problem, have you give me your answer in a sentence using appropriate units. So here, the answer isn't just 4, it's I need 4 liters of the 20% solution. That's what I want to see as part of any word problem. I want to see you defining your variable, as I did here, if you need to. If I define it for you, then you don't have to define it again. I want to see you also giving your answer, again, using appropriate units. So 4 liters, that's how much of the 20% solution do I need.